Okay, so hello and welcome to this first session on your subject, Engineering Geology. So today we're gonna have a lecture on definition, the general geology, its branches, and its allied subjects. So the learning objectives is that you will be able to list the main and allied branches of geology. So we will be able to summarize the scope of geology in various engineering fields, and then describe and recognize various geological phenomena, discuss on each main branches of geology. And you will be able to relate to terminologies relating to geology, subject, and then justify the role and importance of the subject in our civil engineering profession. And then finally, relate with the importance of the subject in the civil engineering profession. So we're going to discuss each of the branches, and uh, each will be related. We will relate it to the civil engineering profession, what is its implication, what is the importance, the significance, and what will be the scope that will be important to your uh, course or profession later on. So we will start with defining what is geology. So geology is actually geo, which means earth. So the root word geo simply means earth, and then as usual, logos is the term for study. So all of the aspects of the earth will be covered in this geology subject: the origin, the age, the interior structure, and its history. So the Earth, of course, has its surface features that are normally subject of physical change and modification. So we have like rivers, mountains, and lakes. And eventually, as I've said, these surface features tends to evolve and be modified. So what you witnessed 5 years ago, so what you see 5 years ago about the mountains, about the rivers, is totally different from what you see now. Probably that has a lot of geological phenomena that is going on these surface features, and those are important aspects when we are working with the earth. Of course, as professional engineers, we always encounter the earth's surface because it is actually the supporting the supporting foundation of ours, of any structure that we are going to build. Okay, so that is why the geology is so important in our study. And of course, we will have the materials making up the earth and the inhabitants of the earth, which tends to be influential. So tends to be influential on those particular changes and modification of our uh, earth or our place. Okay, why geology in engineering? So let me read the slide. Geology is applied to engineering study since engineering works accounts for geological factors in terms of the location, the design, construction, operation, and maintenance. Thus, such recognition of geology to engineering is termed as engineering geology. So, our design is based on the geological parameters most often, and not only that, we are actually using construction materials which are acquired on the earth. Of course, the earth materials are normally construction materials. Okay, so we need to understand what is the composition, or what is good material that could be used in our uh, endeavor in constructing structures. Okay, so it is also important the history. Okay, whether your site is prone to a certain geological phenomena like landslide, or there is a history of faulting or folding of the certain site. So we really need to understand that. Okay, so engineering geologists provide geological and geotechnical recommendations, analysis, and design associated with human development and various types of structures. The realm of the engineering geologist is essentially in the area of the Earth's structure, interactions, or investigations of how the Earth or Earth processes impact human-made structures and human activities. So we now proceed to geology and its main branches. So first we have the physical geology. So from the word itself, physical, so we will be dealing with the study of Earth's rock, minerals, and soils, how they are formed through time, and then complex internal processes like plate tectonics and mountain building have formed these rocks and brought them to the Earth's surface. So physical geology is mainly associated with the plate tectonics. So this is actually a theory in geology. The lithosphere of the Earth is divided into small number of plates, which float and travel independently over the mantle, and much of the Earth's seismic activity occurs at the boundaries of these plates. So Earth is basically a floating ball of slick magma with a thin candy shell of crust around the outside. The crust is broken into large parts, and these parts continue to push into and crunch away at each other. So it is actually those plates are bumping each other or tend to crunch away each other. So by and by I will explain about this phenomena. So here is the picture. So we can see here a series of plates around all over the globe. We have the North America plate, the Caribbean plate, the Cocos plate, Nazca plate, South America plate. We have the Scotch of Antarctica, African, the Indian Australian plate, the Arabian plate. So we also have the Philippine plate, and the Eurasian plate. So it works like a boiling pot with the skin on top, hot rock rises, and cooler, denser rock sinks. So within the mantle, hot areas are rising beneath the ocean ridges. Cooler rocks are sinking beneath the plate convergence zones. Okay, the sinking rocks on the ocean plates are full of water and trap gas that cause some of the rock to melt as it sinks. This molten rock rises to the surface and erupts as volcanoes, outlining the approximate the sinking plate boundaries. We call these boundaries as subduction zone. So this subduction process is happening in many places along the Pacific plate and gives the Pacific Rim its name, the Ring of Fire. So let me explain this through a simple illustration. So basically the movement of the plate is because of what we call the convection currents. Okay, so it is because of the convection currents. Okay. So remember that the inner core, as we go to the center of the Earth, is getting hotter. Okay. So remember that. So a while ago, I have read to you about the plate tectonics theory, that cooler rocks sinks and hotter rocks will tend to go up. So that is why there is movement going on underneath your lithosphere. So the outer layer is actually what we call lithosphere, and then the layer beneath this one is getting hotter. So within this zone, our zone is getting hotter. So this is actually what we call the asthenosphere. So within this lithosphere, there are layers of plates that tends to bump each other or crunch away each other. So let us have some of the terms here about this phenomena. First, we have to identify what are the terms or the names of the plates. Normally, there are two types of plate. First, we have continental crust and the oceanic plate. So continental crust or plate, by the term itself, it is situated on the landmass portion of the Earth, and the oceanic plate are the plates holding the water boundaries of the Earth. So normally, continental crust or plate is made up of granite. And your oceanic plate is usually made of basalt material. So let us take note here that basalt are more denser. So meaning its molecules are more intact, so that it is more heavier than that of the granite. Okay, so there are just two possibilities of these layers, and those are either will have a converging boundary or a diverging boundary. So converging boundary is the movement of these two plates towards each other. So if it is towards each other, it is actually bumping each other or pushing the plates. The plates push each other. Okay, so it is in the compression mode. Okay, for the diverging boundary, it is actually the plate are crunching away from each other. So these two phenomena could occur to both continental crust or between two oceanic plate, or between two continental crust, or between oceanic plate and continental crust. So what are the possibilities? So if we have two continental crusts bumping each other, say these are the two plates bumping each other, so tendency is this certainly will have the same or similar density. So if that is the case, it is likely to be compared to vehicles colliding each other. So therefore, it will form a crumple between these plates. Okay, so there will form a crumple on that plates. So those plates will crumple up because of the bumping effect and form mountains, and actually it will tend to increase the height of the mountain. So the most popular example for this is the Himalayan mountains, where the Mount Everest is situated. So it is actually the collision of Indian and Asian plate. So in fact, because of this phenomena, yearly Mount Everest tends to grow around 0.4 millimeters per year. Okay, so that is the effect of uh, converging boundary between two continental crust or continental plate. But what if we have converging boundary for oceanic plate? Say I'm going to represent that in a blue color. Say we have oceanic plate converging to continental plate. So what is the tendency? So remember that the oceanic plate is composed of basalt, and it is noted that it is more denser and it is more compact, meaning it is more heavier than the continental plate. So the tendency of the oceanic plate is to be pushed underneath the continental plate. So this oceanic plate will tend to go down, and as it will continue to go down, of course the basalt material will tend to be towards the hotter region, and it will certainly reach that point, causing a volcanism effect to the surface of this. So most of the material will go into a thin sphere, and again there will be melting at some point underneath, and then we take note that the hot material will tend to go up, and colder material will tend to sink. So that is why normally between oceanic and continental plate, there will form here volcanoes on the surface that will be the exit of the hot material that is melted from out of the bumping of these two plates. So this is true to the west coast of the United States, wherein it is observed that there are active volcanoes between these two plates. Say we have Mount Rainier as well as Mount St. Helens, that is on the west coast of the United States. And how about if we have oceanic plates that are converging each other? Say, tendency is the material tends to buckle each other. So the cause or the effect of this is also equal to volcanism, since some of the material will tend to melt. And of course, the hotter material will tend to go up, causing volcanism. And this will also cause the formation of island. Okay, because some of this portion will tend to go down, so there will be a concave action on this. So some of the portion will have to go up, so this will form an island. Say if this is the water surface, so the hinge portion of this concave action, say the upper portion, will rise above the water level, and that will be an island, or the formation of the island. So that is a collision between two oceanic plates, or that is a converging boundary between oceanic plates, and it will result to volcanism and island island formation. Okay, so those are the possibilities of converging plate boundaries. How about if it is diverging? So the opposite of converging is diverging. So meaning the plates will tend to crunch away from each other. Say if we have plates here, so it will simply widen the gap between these two plates. So between two oceanic plates, it will cause here spreading, or seafloor spreading. So the practical example here is the Atlantic Ocean is getting bigger and bigger. So that is the seafloor spreading. So in case of two continental crusts, that is moving away from each other, it will just simply cause here a reef valley. Okay, of course it is rift. That's why the term is reef. Okay, so there will be a lower portion on the gap between these two plates, causing this geological feature. Okay, so an example is African rift in Africa. So Rift Valley in Africa is the practical example. So that is the diverging plate boundary. So there is also another phenomenon wherein the plates will just tend to pass over each other. Okay, it will pass over each other. So this is termed as transform boundary. Okay, that is what we call the transform boundary. So this is all about the plate tectonics. That is why some of geological features are formed, like valley, volcanoes, seafloor spreading, the formation of mountain, the formation of islands. So the root cause is what we call the convection currents, wherein because of the hot layer beneath the Earth's surface, there will be a movement. And among this movement, it will facilitate uh, converging boundaries, diverging boundaries, as well as transform boundaries. Okay, so we go back to our slide. Okay, so we can see here now the spreading of the ridge, wherein we have the transform plate boundaries that tends to pass each other. So normally there are volcanoes between the oceanic and uh, continental crust. Okay, so we can see here that the the oceanic plates will tend to go down. Okay, and that will cause volcanism. Okay, so moving on, the evidences of plate tectonics. Okay, so far, uh, this theory is supported by evidences. Number one is the distribution of fossils on different continents. Okay, and secondly, the occurrence of earthquakes. And then number three, continental and ocean floor features, including mountains, volcanoes, faults, and trenches. So the particular evidence is the continents fit together almost like a puzzle pieces, forming Pangaea, or one super continent. So theoretically, the Earth composes of only one landmass. It is called Pangaea. That is 225 million years ago. And after million years passed, say 150 million years ago, it will this a single large mass started to move away from each other, forming a few pieces of land masses, and then it has magnified as the years passes. And truly, if we look at the map, it seems that this uh, continents tends to fit each other. Okay, so that is a particular evidence. And another, that the fossils on different continents are similar to fossils on continents that were once connected. When continents split, different life forms develop. So you can see here in the figure, we have certain uh, fossil of the living organisms. See, the remains of the freshwater reptile Mesosaurus have been found in both South America and Africa. So that theory supports that Africa and South America were once connected. And fossil remains of Sinognathus, a Triassic land reptile approximately 3 meters long, have been found in Argentina and South Africa. Okay, so fossils of plants as well, like fern or Glossopteris, found in all the southern continents, are proof that they were once joined. Okay? So yung mga fossil na yan, wala naman sa north, nasa south lang. And it is interconnected, ano? Okay? And then evidence of the Triassic land reptile Listosaurus has been found in Africa, Antarctica, and India. So when continents are reassembled into Pangea, we find a remarkable alignment of fossil remains for organisms of that age. Organisms that develop later do not follow this pattern. So another one, most continental and oceanic floor features are a result of geological activity and earthquakes along plate boundaries. The exact patterns depend on whether the plates are converging, so being push each other to create mountains, or deep ocean trenches that is diverging, being pulled apart to form new ocean floor at the mid-ocean ridges, or sliding past each other along surface faults. Yung sliding past each other, yun yung transform boundary. So as we can see, if we trace the historical or the occurrence of earthquake, the epicenter is the blue ones, and the volcanoes. So we can see here that those are actually boundaries of the plates. Okay, so the epicenter of the earthquake normally are the boundaries of the plate. And if we're gonna review that, where's the Philippines? The Philippines, here. Here's the Philippines. Okay, there are a lot of earthquake and volcanoes going on within the zone of this. Okay, that is why it is termed as a Pacific Ring of Fire, because it is within the Pacific Ocean. There are a lot of volcanism or volcanic activities as well as seismic activities going on, especially where the Philippines is situated. Okay, so moving on. So physical geology and civil engineering profession. So what is the implication of this physical geology in CE profession? We have geomorphological features of a certain site landscape is a very important data and parameters in civil engineering, especially in the study of geological hazards. So geomorphic meaning the physical attributes like the height, the slope, the layers. So those are important parameters in dealing with the geological hazards such as landslides. Okay, so we also have changes occurring on Earth's surface is a crucial information for a resilient design of structures and for an optimized functionality of structures like dams. So knowing the pattern of the changes in the Earth's surface, we could predict, for example, a surface feature of the Earth like rivers would tend to become dormant at a certain period, meaning it could be at that drought state at a certain point in time. Okay, so something like that. Those are the important significance or the knowledge in geological processes. Okay, so recognition of physical processes of rocks is a great basis on selection of engineering materials in construction. So next is mineralogy. So it is the branch of geology concerned with the study of minerals. So we know that a mineral is naturally occurring, so it will occur without the human intervention. Okay, so it is homogeneous solid with a definite chemical composition and a highly ordered atomic structure. So a homogeneous substance is one that can be divided into repeating units that are exactly the same. So that is why there are a lot of shapes of this geological substance. So this crystal form will come into polyhedral geometric shapes. So there are a lot of patterns. So those patterns are actually formed out of the atomic structure of the minerals. So a diamond would have a certain uh, similar in appearance but different physical attributes like its hardness. Okay, there might be a certain mineral that are similar in appearance, however different strength or durability. So why is that? Because at some point diamond has a good arrangement of the atomic structure. Okay, so it has an intact atomic structure, especially the arrangement. So later on we will look into that. Okay, so petrology is the branch of geology that deals with the origin, composition, structure, and alteration of rocks, which also includes mineralogy, the study of the individual mineral in rocks and its sediment. Okay, so petrology, it is a study of rock. Okay, it is not the study of pet, but it is the study of rock. So as we can see here, the layers of the earth will have series of different material. So the lithosphere composes of crust and uppermost mantle. So it is normally it is 0 to 100 kilometers thick, and beyond that we will be having a more hotter region, see the asthenosphere. It is around 300 to 350 kilometers, and then the liquid and the solid portion on the inner core. Okay, so that is around 6,378 kilometer in radius. So in the figure, the study of petrology is within the crust boundary. The outermost solid part of the earth is made up of different kind of rocks. Okay, so let us have some of the terms here. Lithosphere. So the root word is litho, means rock, and the sphere is means the zone. And the crust surface is uneven with many depression and elevation. So depression, these are lower zones on the Earth's crust, usually filled with bodies of water like lakes, seas, and ocean. So hydrosphere is the zone of lithosphere associated by bodies of water. So just stick to the term that is a hydro, so meaning hydrosphere. It is the zone of lithosphere associated with bodies of water. And then biosphere, it is the zone in the Earth's crust where all living creatures exist. So it could be on the land or lithosphere, or in the bodies of water or the hydrosphere. And of course, we all know that the atmosphere, the layer of the air in which both hydrosphere and lithospheres are enveloped. So if we can diagram that, we have the biosphere could be the tree environment of hydrosphere, lithosphere, or atmosphere. Okay. So what is the importance or the implication of petrology in civil engineering profession? So in many cases, rock has been a part of civil engineering practice. So aside from being utilized as construction materials, rocks are also encountered in mountain engineering like tunneling, slope stabilization, as well as foundation of structures. So next we have the structural geology. Geology is the study of the deformation of the surface and subsurface of the Earth and planetary bodies. This deformation reflects past changes in local and regional stresses and strain and can be used to reconstruct past crustal movements and dynamics. So as we have been discussing, there are movements because of the plates, and this will cause a geologic structure, okay, because of those movements of the plate. So this will cause faults, folds, and unconformity. Faults, a planar or gently curved fracture in the rocks of the Earth's crust where compressional or tensional forces cause relative displacement of the rock on the opposite sides of the fracture. So normally we can see a certain portion of the mountain that there is a discontinuities in it. Okay, so we can observe some cracks or fracture on that certain surfaces. That is because of faults. Okay, so if the failure is brittle, that will have a fault or discontinuities, or what we call failure plane, or usually termed as fault plane. So faults, so fracture. So as the range in length varies from a few centimeters to many hundreds of kilometers, and displacement likewise may range from less than a centimeter to several hundred kilometers along the fracture surface. In some instances, the movement is disturbed over a fault zone composed of many individual faults that occupy a belt hundreds of meters wide. So the geographic distribution of faults varies. Some large areas have almost none, others are cut by innumerable faults. Okay, so before I am going to continue discussing this one, let me reiterate here, say some terms that we need to discuss. Well, faults and faults are normally uh, caused by the movements, okay, caused by the converging and diverging uh, plates. Say a convergent plate boundary, we will have a squeezing effect, which is normally pushing each other, or that is a compression, while divergent plate boundary is having a spread apart phenomenon wherein it is in tension orientation. Then we have a transform plate boundary wherein we have we have friction phenomena between rock layers. So when that happens, your layer will become thinner and thinner. So this is actually a shear effect. Okay. And actually in strength of materials, compression, tension, and shear are type of stresses. Okay. So when a certain material stress, it will result to strain or deformation. Okay, it is actually the change in shape in the form of rock. So there are three types of deformation here, just like in the principle of the mechanics of deformable bodies. There will be brittle deformation, the plastic or ductile deformation, and then we have the elastic deformation. Okay, so let me demonstrate that out of this stick here. First, the plastic or ductile deformation. Okay, so if we have a plastic deformation, we apply as slowly to this certain material, okay, and release the loading. It came to a permanent set. Okay, so it came to a permanent set. So meaning it has already reached the elastic limit. Okay, so the elastic limit is the tendency of this material to go back to its original shape when the loading is released. But this time, in this case, we can see here that it has a permanent curve. So meaning it has not returned to its original shape. Okay. So for elastic deformation, let us have the same stick here. If I'm going to apply here certain load and release it, it will go back to the original shape. So meaning uh, the elastic limit could tolerate the loading so that it will not set to a permanent deformation. So it will return to its original shape. Okay. So for brittle deformation, so for brittle, which is true to the rock, because a rock is normally has a slight elastic properties. That is why normally it is mostly it is of brittle deformation, especially when the loading is so quick and under cold conditions. So like this, brittle deformation. So it breaks right away. Okay. So the deformation is so quick. Okay, that is so brittle. It will not tend to have an opportunity to go back to its original shape, or at least bend itself. So brittle deformation is actually this is uh, fault. Okay. When we have a plastic or ductile deformation, this is fold. Okay. And elastic deformation normally is rebound, or meaning uh, the deformation is not evident because as the loading was released, strain will also be released. Okay. So there are some aspects that characterize these three types of deformation. So if you observe a while ago, brittle deformation is characterized by a quick loading that is being applied that caused the sudden breakage of the material, while plastic or ductile deformation it required uh, a slow application of the loading over a long period of time. So parang hinihilot mo yung material in order to come up. Of course, the failure is uh, not sudden, or meaning it is plastic in nature. So by the way, temperature has also significant implications on these two, the effect of brittle deformation and plastic or ductile deformation. So if we have a brittle, of course, a cold temperature would tend to make the material brittle, and a warmer temperature could also enhance its ductility. So that is why in layer of the earth, the outermost layer, say the lithosphere, so normally when there is a diverging converging plate boundaries, or a bumping plates, faults are found on the upper layer of the crust, or the earth's crust, and faults are normally found beneath this outer layer. Why? It is because that the outer portion is colder and the lower portion is warmer. So there will be a ductile failure here. So the layers of the rock will tend to be fold, okay, on this lower portion, and tends to be fault or discontinuities on the topmost layer. See, those are faults and faults. So we can actually recognize faults normally not on the map view, but in cross-sectional or side view of the mountain or a certain rock, of course. And faults are actually discontinuities on rocks, okay? So it can be classified into slip faults. There are actually 3 types. First, we have strike slip fault. Then we have the deep slip fault, and then the oblique slip fault. So a strike slip fault is a discontinuity that would have vertical slice on the discontinuity. So what I mean is, if we have here a cross section, so let's make here a cross section. A strike slip failure is a failure that the slice on the failure plane is only on the vertical. Okay, it's only on the vertical. Okay, so say let me shade this portion, as we can see that the strike slip fault is that the cutting section is only having a vertical orientation on the slip. Okay, so when we have a deep slip fault, it will include now a diagonal orientation of the slip fault. Say if we have this cross section, we will be having a diagonal orientation of the cut section of the failure slip. Okay, so meaning the strike slip fault will just be always vertical. However, if we have a deep slip fault, there will be a diagonal orientation of the slip fault. So let me shade this one. So for the oblique slip fault is just the combination of strike slip fault and deep slip fault. Okay. So for the deep slip fault, it would include now a hanging wall and a footwall. So I think there is a illustration here for that one. Okay. So we have here a hanging wall and a footwall. A hanging wall and a footwall. And a hanging wall. So the strike slip fault has no hanging wall and footwall. So because of the diagonal, there will be a certain block that will be resting, okay, that will be resting to a certain wedge of the block, and that plate or that material that is resting over the failure slip or riding over the failure slip, that is what we call the hanging wall. Okay, and the point where it is riding, that is the footwall, or it's actually carrying the hanging wall. Okay, so here the inclination is like this, so therefore this block here is actually rides into this failure plane. So here just the same, we have here a failure slip. So actually this is what we call thrust fault orientation, meaning it is almost horizontal, and normally this is unrecognizable because the failure slip is almost horizontal. Okay, so you cannot easily recognize that one. Okay, so there will be a hanging wall and a footwall. So we have here the normal fault or the tensional, the reverse fault or compressional, the thrust fault, compressional, and the strike slip fault or the shear. So what is the meaning of the normal fault? So when we say normal fault, it is actually dependent on the action of the gravity, because that is a normal phenomena. The gravity is a normal condition within Earth's surface. So if we are going to pull this apart, okay, tensional, okay, so pulling that apart would mean by action of gravity, the hanging wall will just be going down because of the action of gravity. So the force itself will have to separate the footwall to the hanging wall. That is why the hanging wall will just go down. Okay, that is why it is termed as normal fault, because it is the effect of the normal phenomena, which is the gravity. While in the reverse fault, compressional, meaning these two structure here will bump each other, so that there will be a wedge action between these two, and the cause of the wedge action between the two is now the force itself. Okay? That is the reverse fault or the compressional fault. Okay, so the thrust fault, again, this is a compressional. However, the fault line or the slip could be hardly recognized because it is almost horizontal. Okay, and then the strike slip fault, the shear, it is the frictional phenomena, okay, between the two uh, structure. So those are the principles in structural geology, especially in faults. Okay, so we have reverse faulting, the normal faulting, and the reverse faulting is caused by the force itself, and the normal faulting is caused by the separation and the action of gravity. Okay, for the faults, this is lack of original planar surfaces such as sedimentary strata that are bent or curved during permanent deformation. So this is experience or occurring because of a strain that is being applied over a long duration, just as demonstrated a while ago when we have a slower application of the stress over a long period of time. It will have a plastic type of deformation, so that will cause a folding. So now the point of the highest point and the lowest point will be having on the hinge zone or the hinge points. So how to determine the hinge points? Simple. If I have here a paper and say I'm going to hang this paper to a certain sampayan or support here, okay, so this is actually the hinge point of the structural fold. Okay, so there is also parts of the fold. See, this is the fold. If we have here a U shape, the U shape for portion is what we call sink line, and then the A shape portion will be termed as anticline. Okay, so both could be tilted. Okay, so it may be that this A shape and U shape will be tilted according to the activities of the folds. So the terms here, hinge is the line joining the points of maximum curvature on a folded surface. So crest represents the highest point of the fold surface. Throw represents the lowest point of the fold surface. And then the inflection point, the point where the concavity reverses on a fold. So take note that there will be two concave here. It is a concave upward and a concave downward. So this transition point here is what we call inflection point. Okay, so the point where the concavity reverses the fold. So here we can see in the figure an example of structural geology or the faults. So another phenomena on structural geology is the unconformity. So it is a buried erosional or non-depositional surface that separates two different age rock masses or strata, indicating that the deposition of sediment was not continuous. The older layer was generally exposed to erosion for an interval time before the younger layer was deposed, but the term is used to describe any break in the sedimentary geological records. So unconformity, there is an indication of geological agents wherein or erosion or deposition, degradation occurs. So all of this will be discussed on the next session we will have. Okay, so for the meantime, we will end up to structural geology faults. So we are actually discussing the structural geology here, and then later on we will be expounding to uh, main other main branches of geology as well as its allied fields. So this ends now our discussion for today. So thank you for listening and see you on the next session.